Hello and welcome back to Electrical Fundamentals. In this presentation, we'll be looking at an introduction to three-phase circuits. It's important to note that I will only be looking at balanced three-phase circuits, in which all line currents are the same value. So there won't be any difference in the lines, so there won't be any neutral currents. We'll be looking at both line and phase values for delta and Y configurations for both voltage and current. So with that, let's get started. Nikola Tesla was the first one to work with polyphase AC systems. And he observed that a three-phase system was the most efficient way to produce, transmit, and consume electricity. When you have a three-phase system, it's unlike a single-phase system. When you have a single-phase AC power, the single phase pulsates and falls to zero. Whereas in a three-phase system, the power never really falls to zero. The power delivery to the load is the same at any point or any instant. This provides a much improved operating characteristic for any three-phase machine. This allows us to have much smaller equipment. Also, because you have constant power, you can also have a reduction in the size of your conductors feeding your three-phase systems. We will look at a couple of different three-phase systems, as stated, the delta and the Y. There are many different variants and subvariants that will not be included in this presentation. But for the most part, a three-phase system will either have 3 or 4 conductors, depending on the configuration. We usually label those conductors as A, B, and C, or as 1, 2, and 3. Here in Canada, we typically use red, black, and blue for our 3 phases. There are other exceptions and other applications where the colors do signify a certain specific application, such as emergency backup systems, which you may find in a hospital. So for the most part, I'll be looking at A, B, and C, or 1, 2, and 3, and red, black, and blue in that order. Our three-phase system has 3 individual HOTs, or feeds. We call these lines, where each voltage is out of phase with each other by 120 degrees. If we take 360 divided by 3, that means each voltage is equally spread apart by 120 degrees. This is quite significant when you go to look at the vector summing of 2 of the voltages together. If we look at our 3 voltages that are separated by 120 volts, and then we just look across the top of each, you can see where the voltage never reaches 0 on the positive alternations. Then if you look on the negative alternations, you can see also there the voltage never reaches 0. If you examine it even closer, you can see when this sine wave is at its peak, that these 2 negative alternations are at their lowest. So even when these 2 alternations are at their lowest, I'm at my maximum voltage here. If you continue to look at it a bit more, and you look at this little area in here, and basically that area is where one alternation is coming down and the next alternation is going up. If you were to take that area in there, you would realize that it would fill in this area in here. And this is one of the major advantages of three-phase, is that not only does the voltage never go to 0, as we see going across the top, that even when it is at its lowest point, as in here, the overlap of the two voltages will actually come together to fill in the valley. Filling it in, giving us a constant continuous push in a negative voltage and a constant continuous push in the positive. So basically, when it comes to three-phase, we are constantly, continuously pushing both in a negative alternation and a positive alternation. This is what makes them so efficient. The voltage not only never falls to zero, when you average it out, it turns out to be a constant, continuous power delivery. Let's take a quick moment to look and see how our voltage is generated in our three-phase system. Here we have a set of magnetic poles, a north and a south. Inside our rotating assembly in the middle here, we have phase A, B, and C. And again, they're all separated. These represent coils that will rotate inside the magnetic field. We know that from our previous discussions that when a wire cuts a field, it generates a voltage. So as our coils spin around inside our magnetic field, our first set of coils, 1 or A, is going to generate an alternating sine wave. Now our second set of coils, or B, are 120 degrees out of phase, or angular degrees, from A. And so now you can see that B starts about 120 degrees after A. And likewise with our third phase, C. C will start 120 degrees after B. Or in this case, it sort of leads A by 120 degrees. So there's a 120 degree separation between C and B, and also 120 degrees of separation between C and A. Again, they're equally spread out. As our rotor continues to spin, it will generate a continuous alternating sine wave. And this is what generates our three-phase power. Now let's take a look at the significance of the square root of 3, or root 3, in three-phase relationships. When we go back and think about our Ohm's law discussions, and we define voltage, we said voltage was the difference in charge between 2 points. Now we have 2 points, voltage of the alternating sine wave A and the voltage of alternating sine wave B. Now when examining alternating voltages, we always look at a moment in time and we look at the RMS value. Here in Eastern Canada, one of our standard voltages is 120 volts. So if each of these sine waves represents 120 volts and we wanted to add them together, we would take 120 volts and we'll use A as our reference, and we'll say it's at 0 degrees. And then we'll take our second 120 volts, which is voltage B, but it's at a 120 degree angle to A. So if we want to know what the total voltage was of those two voltages, we would have to vector sum voltage A with voltage B, which means we need a little bit of trig to calculate that out. Since this is not a right angle triangle, we cannot simply use Pythagorean's theorem. We have to break voltage B down into its vector components, or its x and y components. We can do that very easily by looking at that 120 volt angle there, or vector, and break it down into its x and y components. Since the two voltages are 120 degrees separated, and if we carry on the green line so that it's in line with the red, that means the angle in there would be 60 degrees. We know that the black hypotenuse is 120 volt magnitude, and the angle in there is 60 degrees. We can now use trig to solve the x and y components for that 120 volt vector at 120 degrees, where the opposite side will work out to be 103.923 volts, and our adjacent side will work out to be 60 volts. We can now use the much larger triangle that we just created in order to solve for the gray hypotenuse. So we add 120 to 60. That makes that side 180 degrees. And again, our y side will work out to be 103.923 volts. We can now use Pythagorean's theorem to solve for the hypotenuse, which in this case works out to be 207.48609 volts. Now it might seem a little silly that I kept all of those decimals. Here in Canada, we say that our nominal three-phase voltage is 120.208, and you'd be perfectly fine by rounding that up. But if you don't round those numbers at all, and you make a comparison between the hypotenuse of 207.48609 to any one of the two sides we started with, 120 volts, it turns out the hypotenuse is a perfect relationship to either one of those 120 volt sides by a factor of √3. So anytime you have two sides that are exactly the same, which is in this case 120 plus 120, the hypotenuse will be larger, or the total voltage, in this case, of any two phases at 120 degrees, will always work out to be any side times √3. And this is the basis for easily solving three-phase balanced systems. Let's look into it a little bit further. Now that you know where the importance of √3 comes from. There are two main types of configurations that we will be looking at. One is the Y configuration. And again, we call this a Y because it looks like the letter Y. I'm going to use the standard of labeling the three lines as A, B, and C. You could easily label them as 1, 2, and 3. The second configuration that we will look at today is the delta. And again, it's after the Greek letter delta. Again, I'll be using A, B, and C, but you could easily use 1, 2, and 3. Y configurations can be a three-phase 4-wire or a three-phase 3-wire. Where does the fourth wire come in, you say? Well, where the three phases join together in the middle, in here. We can use that as a balancing point, and we can turn that into a neutral. So most of the time, not always, but most of the time when you have a three-phase 4-wire system, we are talking about a Y configuration. Most of the time, not always. Deltas are a three-phase 3-wire system. Now a Y can be a three-phase 3-wire. And you can also have split deltas and high lag deltas, which can be a three-phase 4-wire system. But I will not be covering any of those specialty configurations in this. So let's take a look at a Y configuration. Here we have 3 resistors connected in a Y configuration. I've tilted it ever so slightly just to make it easier to draw. You can ignore the circle's significance for now. The only reason I've added this circle is because I want you to think about what's inside the circle. When these 3 resistors or loads are inside the circle, we are talking about phase values. A phase value is anything that is inside the shape. In this case, the shape being a Y configuration. So I have phase A, phase B, and phase C. Equally, I could say phase 1, phase 2, phase 3. Again, I color coordinated them as red, black, and blue. Now, when I take wires out to feed each of these phases, you'll see that the wires are outside the circle, or outside the shape. These are what we refer to as our line values. And you can think about your line values as your feeder lines. And again, they are independent of the shape. I could easily pull out the Y configuration and put in a delta configuration, and the lines would not be any different. But the values inside, the phase values, would change, because the shape would change inside the circle. So it's important to remember that phase values are inside and line values are outside. Here, between A and C, we have a line value from A to C. This would be our 208 volts that we calculated earlier. Again, Y's can be 3-phase 4-wire or 3-phase 3-wire. In order to be a 4-wire system, we need to add a neutral to a common point, so that if any of the currents are unbalanced, the neutral can carry the unbalanced load. Between the neutral and any single one of the lines is also considered a phase value, because if you trace your finger along from the neutral through, you can see that it only covers phase B. Whereas if you go from line A to line C, you'll be going across 2 phases. 2 phases make up a line value. Same as we calculated before, 120 volts plus 120 volts at 120 degrees separation would give us our 207.46 volts. If we were to go between line A and line B, you would say in order to get from there, I would again have to go through 2 phases. 2 phases added together give me a line value in a Y configuration. So that's how voltages work in a Y configuration. The line value is between any 2 feeder lines. The phase values, well, those are inside the shape. The line values are outside external of the shape. In a Y system, the line voltage is higher than any phase by a factor of √3, as we calculated earlier, because the line value is made up of 2 phases. And any 2 lines, A and C, or A and B, or B and C, will be made up of 2 phases. So our line value, E line, is equal to E phase times √3, or √3 E phase. If we have a line value, we can easily find a phase value, because a phase value is smaller than a line value by √3. So let's take a look at another set of line and phase values. Again, our relationships is E line is equal to root 3 E phase. Or our phase is smaller than the line by a factor of root 3. So if we have a line value of 600 volts, if we take 600 volts and divide by root 3, we would get approximately 347 volts across our phase. So too, if we were to go across any one phase and multiply that by root 3, we would get back to our 600 volt line value. These are nominally stated voltages. 347, 600 is a standard Canadian three-phase commercial voltage. Well, how about currents in a Y configuration? Well, I line is equal to I phase in a Y configuration. Because as my line current comes in, all of that line current is forced through the phase. So that results in a line current being the same as a phase current because there's no place for it to branch off. Once it gets to the center node, then the current will equally split up between phase C and B. Any unbalanced current would then be returned on the neutral. But the only thing you really need to remember for this is that a line current and a phase current are the same in a Y configuration. So here, if I have 5 amps coming in on the line, I will also have 5 amps going through the phase. Line and phase currents are the same in a Y connection. So let's review our Y connection. In a Y connection, our line current and our phase current are the same. As you can see here, the current leaving phase B is also the same current that would be going out through line B. In a Y-connected system, the line voltage is larger by a factor of root 3 over the phase, where the phase is smaller than the line by a factor of root 3. So here we have line AC, and that is made up of the two voltages of E phase A and E phase C. Again, these are separated by 120 degrees. So this voltage plus voltage C at 120 degrees will result in a line value that is root 3 larger than either of them. You can sort of think of your Y connection sort of like a series circuit. If you remember your principles for series circuits, current is common. And that's what happens in a Y connection. My line current and my phase current are the same. And sort of like series, in a Y connection, the voltages add, where my two phase voltages add together to give me my line value. So in that sense, Y's are sort of like series. So let's do a sample calculation. Let's find all the line and phase values for this simple Y connection. Given that you have a 600 volt line value at 60 Hertz, and you've got 3 inductive loads connected in a Y configuration, and each of those phase inductive loads will be 69.4 ohms. Since our loads are inside the shape and they're a phase value, we are going to need a phase voltage. So that's the first thing you'll need to calculate. Our phase values are smaller than our line values by a factor of √3. 600 divided by √3, that'll actually give us 346.41 volts. 346.41. But I have given the stated nominal value of 347, which is an acceptable answer. Now that we have our phase voltage and we have a phasor inductive load, we can find out what our phase current is. 347 divided by 69.4, well, that's going to give us 5 amps per phase. But our Y being similar to a series circuit, our line value and our phase current are both the same. So our line current and our phase current will be approximately 5 amps, depending on how you round. Early in the discussion, we said that there were 2 different configurations. We've now discussed the Y configuration, which is sort of like series. That leaves us to have a discussion about the delta configuration. Much like as the Y was sort of like a series, you can think of the delta as sort of like a parallel. Follow along and you'll see what I mean. Let's take a look at delta voltages first. Here, we've connected 3 resistors in a delta configuration. Again, I'm going to draw a circle around the delta. And everything that's inside the circle is a phase value. So I have phase A, phase B, and phase C. Again, I could have easily used 1, 2, and 3. When I bring my lines out to feed my phases, again, these are now outside the shape, so now these are my line values. For the most part, most delta loads are a 3-phase, 3-wire. When you look at the line values and bring it inside, you can see that line AC is directly across just phase C. So too, if I was to look at line A to B, you would see that line AB is just across phase A. Or if I was to look at line CB, that would be across just phase B. In a delta configuration, the line value and the phase value are the same, much as it is similarly or sort of like parallel. Now let's take a look at our currents in a delta configuration. As our current comes in on line A and gets to this node, it has to break up so that our phase currents are actually smaller than our line current. And you guessed it, the relationship is 120 degrees of separation. Because of the 120 degrees of separation, it's a factor of √3, where our phase current is smaller than our line current by a factor of √3. Or when I add 2 phase currents together at 120 degrees separation, our line current is bigger than any one phase by a factor of √3. 2 identical values added together at 120 degrees is simply a multiple of √3. Let me rephrase that. Any 2 identical values separated by 120 degrees. The vector sum of those two same things at 120 degrees separation will result in a multiple of root 3. There you go. So when I take a look at my line current coming in, and I have 20 amps coming in, that current coming in will get to the node and break up. So if I take my 20 amps and divide by root 3, we will end up with approximately 11.54 amps in each phase. Again, our line current is bigger than any phase by a factor of root 3. So let's review our delta. In a delta, line and phase voltages are the same, where our line value is directly across any phase. So those two voltages have to be the same. When it comes to current, when two phase currents come together, they will make up a line current. So our line current is bigger than a phase by a factor of root 3. Or our phase is smaller than our line by a factor of root 3. Again, that's all because there's 120 degrees separation between each of the voltages coming in. You can sort of think of your delta like a parallel. And again, if you recall your rules or tenets for a parallel, voltage is common, E line and E phase, but currents add, where two phases at 120 degrees, if identical, is merely a factor of root 3. So let's calculate all the phase and line voltages and currents for this simple delta. Again, let's use 600 volts, 60 hertz as our standard line voltage. We'll have a delta connected load of 51.96 ohms. And again, these resistors are connected inside the shape, so these are phase values. Since I have a phase connected load, I need a phase voltage, but it's a delta. And in a delta, E phase is equal to E line. So our phase voltage is 600 volts as well. Now that we have our phase voltage and our phase load, we can calculate our phase current, which in this case works out to be 11.547 amps. Now the current in A and B are going to come together to give us the line current at B. So again, there'd be 120 degrees of separation. We could go through the vector summation of working that all out algebraically with trigonometry. But since they're both the same, we can just use our factor of root 3. 11.54 multiplied by the square root of 3. Well, that'll give us 20 amps on our line. Now that we've looked at voltage and current in three-phase systems, how about power? How is that calculated in a three-phase system? Well, we have three loads inside our phase, inside our shape. Doesn't matter if it's a delta or a Y. Each of them have three loads. If we look at each individual phase and we calculate the power in one phase, well, that would just be E phase times I phase. And since there are three of them, we know that power always adds. Our total power would just be 3 times E phase I phase. Another way to look at it is that if I added two phases together, I would end up with a line. And so that would be root 3 E phase I phase would give us a line value. If I wanted to add a third line to the other two, I'd have to multiply it by root 3 again, because there'd be an additional 120 degrees of separation. So if I'm using line values, our total power equals root 3 E line I line. Again, to go from a phase value to a line value, multiply by root 3, that gets us to our line values. And if I want to add an additional one to each of those, again, it would be 120 degrees of separation. So I would have to root 3 each of the lines again. So to simplify, I can calculate the power in either a delta or a Y by using either of those two formulas, where my total power is equal to 3 E phase I phase, or the total power is equal to root 3 E line I line. Now those values might change a little bit depending on how you round. So let's go back to our sample Y problem and calculate out the inductive reactive power in VARs. Earlier, I had said that the phase voltage was 347 and the current was 5 amps. And within a reasonable margin of rounding, that is acceptable. And 347 is considered the nominal three-phase voltage for 600 volts line, which did result in 5 amps. But I'm going to go back and recalculate that without rounding. If you take your 600 volts and divide it by root 3, you'll actually end up with 346.41 volts. That actually results in a line current of 4.9915 amps, not 5. So you can see where it's not really a major difference. It's quite slight, actually. But when we compare our two power formulas, and again, line current and phase current are the same in a Y. Our voltages are different. When we look at our inductive reactive power, Q, we can calculate it by using root 3 E line I line, which is root 3 multiplied by 600 volts, by our unrounded current, will give us 5187.3 VARs of inductive reactive power. We could equally as easily have calculated that out to be root 3 E phase I phase, which, when multiplied out, gives us an identical answer of 5187.3 VARs. If you use the rounded values of 347 and 5 amps, those values will change ever so slightly. Now how about in our delta configuration? In our delta, our line voltage and our phase voltage are the same, 600 volts, which resulted in a current, and I said approximately 11.547, and that's a fairly accurate approximation, will result in a line current of 20 amps. Since this is a resistive load, we can use the letter P for power and watts, true power. And if we root 3 E line I line these values, we end up with 20,784 watts. If we use our phase values, you calculate the power in one phase and multiply it by 3 because there's 3 phases, you again end up with the same identical answer of 20,784 watts. So what's our takeaways from all this? Well, there's two main configurations. There's the delta and the Y configuration. The delta is typically a three-phase, three-wire system. Typically. It is not parallel, but it sort of is like parallel if you want to remember the basic principles for a delta. Just like parallel, the line voltage and the phase voltage are the same. If our two phase currents are the same value at 120 degrees of separation, then our line current will be bigger than our phase by a factor of √3. So too, if our delta connected loads are the same, then our phase current will be smaller than our line current by a factor of √3. Our Y connected load can be a three-phase, three-wire or a three-phase, four-wire. And it sort of acts like series. It's not series, but it's sort of like series. Sort of like series in the sense that the line current and the phase current are the same. And the two phase currents will add together to give us a line current. If they are balanced and the same at 120 degrees of separation, then my line voltage will be bigger than any one phase by a factor of √3. If my loads are the same and the system is balanced, then my phase voltage will be smaller than my line voltage by a factor of √3. If we wish to calculate our power in our three-phase system, then our total power is equal to √3 E line I line, or equally we can calculate it by our total power is equal to our total power is equal to 3 E phase I phase. That concludes this presentation on Introduction to Three-Phase Systems. I hope you've gleaned a little bit of insight into the efficiencies of three-phase, why it's more efficient, and how to calculate line and phase voltages and currents, as well as power in a three-phase system. Thanks for watching.